All right, here we go. Practice problems. We're going to work through, let's see, 1, 2, 3, 4 of them in this video here. And they are going to span the gamut of all the kinds of equilibrium stuff we've looked at in this chapter. So the first one here is a very strange reaction with iodine. So we have iodine reacting with iodide to make triiodide, I guess. Yeah, triiodide ion. Very strange reaction. So this question says, if a solution with the concentration of I2 and I minus both equal to 1 times 10 to the negative third, before reaction gives an equilibrium concentration of 6.61 times 10 to the negative 4, I2, what is the equilibrium constant for the reaction? All right, I want you to work through this one. And I'm going to go ahead and actually, if you want to try to work through it without a hint, excuse me, without a hint, pause the video now, try to work through it. If you want a hint, here it is. Notice we're given an equilibrium concentration. There should be no x's in this problem. No x's here. Everything should be a known value. So if you've taken the hint now, go and try to work through the problem. So pause the video now. Okay, so in this problem, go ahead and write my ICE table, because we're going to have an ICE table for every problem here. So I have my initial change equilibrium, I have my I2, I minus, and I3 minus. I am told that I have 1 times 10 to the negative third of both of these, and I am not told anything about the I3 minus, and so I'm assuming I have none of that. But I am told that at equilibrium, I have 6.61 times 10 to the negative 4 of I2. So, I know the initial and the equilibrium concentrations of I2, so I can work out that change. So let's say 6.61 times 10 to the negative 4 minus 1 times 10 to the negative 3. This molecule decreased by 3.39 times 10 to the negative 4. What that tells me is this one also decreased by 3.39 times 10 to the negative 4, and this one increased by 3.39 times 10 to the negative 4. Just stoichiometry. That's all that is. Whatever change happened to I2, the same thing happened to I minus, and the same numerical value but opposite in sign happened to the I3. So that tells me this is going to be 3.39 times 10 to the negative 4, since we started at 0. And this one, since it started exactly the same as the I2, is also going to be 6.61 times 10 to the negative 4. So I have all my equilibrium concentrations. So the last thing I need to do is just plug those in. So I'm going to have 3.39 times 10 to the negative 4. It's my one and only product. And since it's just 1 here, I would just have a 1 here, but I'll leave that out. Those are normally left out. And down in the denominator, I will have 6.61 times 10 to the negative 4 squared. So if I do that math, it is 776, we'll say. 775.8839699, but we'll go with 776. All right. So again, the key here was realizing that we already have an equilibrium concentration. There's no need to deal with unknowns because we know the value for the change of one thing. And if you know the value of one of the changes and you know the reaction that's taking place, you can use stoichiometry to work out the rest. Okay, let's look at the next one here. Nitrogen oxides are air pollutants produced by the reaction of nitrogen and oxygen at high temperatures. At 2000 degrees C, the value of the equilibrium constant for the reaction, it's actually the same reaction we saw a minute ago, is 4.1 times 10 to the negative 4. Find the concentrations of NO in an equilibrium mixture with air at 1 atmosphere pressure at this temperature. In air, nitrogen has a concentration of 0.036, and oxygen is 0.0089. Alright, so I want you to go ahead and give this one a try as well. The only hint that I will give you here is that we are not given any equilibrium concentrations here. So we're asked to find the concentration of NO at equilibrium, and it's not entirely obvious in the question, but it's not saying that these are the concentrations at equilibrium. So this is the concentration just in air normally. So this is where the initial states for the N2 and the O2, and we would have 0 of the NO. So go ahead and pause the video now and see if you can find that equilibrium concentration. Okay. So, we were told we're starting with 0.036 and 0.0089, and we have none of that. And we're also told that K is 4.1 times 10 to the negative 4. All right. So, in this situation, because we have no equilibrium information other than the constant, we will be using x. So we know that this is going to decrease by some amount x. This is going to decrease by the same amount, x. And this is going to increase by 2x. So that means that at equilibrium, we will have 2x of the NO, and we will have 0.036 minus x, and 0.0089 minus x. All right, so I probably should have drawn this smaller because I think I'm going to run out of space. So we have 4.1 times 10 to the negative 4. That is our K value, and that is equal to products over reactants. So we're going to have 2x squared, because again it has a coefficient of 2 here, and I know some students get confused here. It's like, wait, we're double counting the 2. Yes, we are. We're supposed to. So the 2 affects the concentration, and the 2 affects the coefficient, the exponent here. It is supposed to be in both places. So we have 2x squared. That's our product. And then in the reactant side here, we have 0.036 minus x and 0.0089 minus x. Our lives would be much simpler if we could make the x's small assumption here. And why don't we go ahead and make the assumption? But if I remember correctly, I don't think we're going to be able to keep it. So if we make the x's small assumption, that's going to make this and this, these two x's, just go away, which would leave us with 0.036 times 0.0089 in the denominator. which is 3.2 times 10 to the negative 4, essentially. So, just for the sake of expedience here, I'm going to go ahead and work through this algebra real quick. So I'm going to multiply 3.2 times 10 to the negative 4 by the 4.1 times 10 to the negative 4. And then I'm going to take the square root of that to get rid of the square here. And then I'll divide by 2. So using the x is small assumption, I got that x is 1.81 times 10 to the negative 4. That's what I got from that. So what I'm going to do now is I'm going to do that check that we talked about. Take the x value, and I'm going to divide it by the thing that I would have subtracted it from. That would be and I'm going to use the smaller one, not the bigger one. So it would be 0.0089. Multiply that by 100%. And, oh, actually, I think it is going to work. I don't think that it should. Let me double check what I'm doing here. Doesn't seem like that should work, but it says that it is. It says I'm getting 2%, which would be acceptable, but those seem too close together. I'm going to double check my math here real quick. That times that. Sorry to make you hear me whispering to myself. Okay. No, I guess it does work. Okay. It's fairly close. If the concentration had been much lower, I don't think that it would have worked. But unless I'm just really messing up the math somewhere and I'm just not catching it because it's fairly late and I'm not thinking straight, it does seem to be giving me 2% as the value, which is within the acceptable range. Because remember, up to 5% is acceptable. So actually, we can go ahead and use the x is small assumption. So this would actually be our value for x, which means that our goal, what we're trying to find, the equilibrium concentration, is just 2 times that. So we have 1.81 times 10 to the negative 4 times 2, which is 3.62 times 10 to the negative 4 molar. Okay. So, moving on from that one, we have here is another equilibrium problem that is kind of unique, and then we have phosphorus and chlorine reacting in interesting ways. So we have, under certain conditions, the equilibrium constant for the decomposition of PCl5 into PCl3 and chlorine gas is 0.0211. What are the equilibrium concentrations of all 3 of those if the initial concentration of PCl5 is 1 molar? So now this is another one of those where I'm questioning whether or not we'll be able to use the x is small assumption. But we'll go ahead and check it just to see. And if you would like to work this one through on your own, obviously you want to pause the video now and see if you can figure it out without me working through it for you. All right. So we only have one reactant here. This is decomposing into the other 2. It's the reaction that's happening here. And we're told that we're starting with 1 molar PCl5. We're not given any information about initial concentrations of the other two, so we're going to assume that we have none. We're also told that K is 0.0211. So this is all the information we're given at this point. So because we're not given any equilibrium concentrations, once again we're going to go straight to our x values here. So we're going to have minus x for this and plus x for both of those, since we have just one of each, or just one of everything, disappearing and appearing. So that means we're going to have 1 minus x, x, and x as our equilibrium concentrations. So if we go ahead and plug all of those in, that is equal to products over reactants. Products are x squared. 1 minus x is the denominator there. Now obviously the math here isn't horrendous by any means, but you would still, because you have the x squared and you have the minus x, like you would still need to pull out that quadratic formula to get this solved. So let's go ahead and just try the x is small assumption and see what happens. So if we just ignore the x here, we would be multiplying both sides by 1 to get rid of this, which is to say that we wouldn't change it at all. And so we would have 0.0211 and take the square root of it to get rid of the square on the x on the other side. So we're taking the square root of both sides. And that would give us x is equal to 0.145. And so if we check our x is small assumption, I don't think it's going to work. So we have 0.145 divided by 1, which is just going to end up being 0.145 times 100% is going to give us 14.5%. Yep, that is not okay. That is too large of an error. We cannot use the assumption for this problem, so we will have to do the math. Now, I wish there was a way for you to see my calculator, or for me to display a calculator or something on here, because the way that I prefer to work through these kinds of problems is using the equation solver, and I just don't think there's any way that I can do that over audio only, explain how to work through it. So what I'm going to do is I'm just going to type this into my calculator real quick just to get the answer. And if you at home doing this know how to use the equation solver, you can do that as well. If you are comfortable enough and you want to go ahead and do the algebra, awesome, do the algebra. If you're in neither of those groups, feel free to ask me about it the next time you see me in class, and I will show you how to use the solver function on your TI calculator, assuming you have a graphing TI calculator. So what I'm getting from my calculator for the value for x is 0.135. So that's a definite difference between the x that I got making the assumption and the x that I got without making the assumption. So again, that's bad x. So then, now I'm ready to give my final answer. So the question asked, what are the equilibrium concentrations of all three of those? Well, this is the concentration of those two. And then the concentration of the PCl5 would just be 1 minus 0.135. And so that would be, oops, sorry, put the decimal point in the wrong spot. 0.865. And those are our equilibrium concentrations. Alright, I hope that one was clearer than some other ones that we've done in the past. I know we're doing a lot of practice problems in this video, but hopefully it's helpful for you to see me work through them, so it'll help you get through homework and stuff like that. We have our last one here for this video. It says, what are the concentrations at equilibrium of a 0.15 molar solution of HCN given that reaction and the Kc value? So once again, we're given initial concentration and the K value and no equilibrium information. So we're going to have X in our equation. So we have our initial change equilibrium. Once again, if you want to work through this on your own, which I would highly encourage, go ahead and pause the video now. Come back when you think you've got it worked out and see if you did it the same way that I did. So, we're told that we're starting with 0.15 molar HCN. We're not given any information about these, so we're assuming we have none. Very standard procedure now, hopefully, at least it's standard procedure now. We're losing some amount X of this and gaining the same amount of the other two things. And so we will end up with 0.15 minus X, X, and X. I'm going to tell you right now, we're using the X is small assumption, and it's going to be perfectly legitimate to use, because that is a minuscule K value and a decently large concentration. They are 9 orders of magnitude apart, and so they're going to be fine. It's going to work out. So let's go ahead and plug in what we know. We know Kc is equal to 4.9 times 10 to the negative 10. That's given to us. And we know that that is equal to products over reactants, which in this case is X squared, because both H plus and Cn minus are just X at equilibrium. And this is going to be 0.115. There would be a minus X here, but we're ignoring it, because again, we're making the X a small assumption. And so if we do the math here, 4.9 times 10 to the negative 10 times 0.115, and then take the square root of that to get rid of the X squared, we'd be left just with X. And we find that X is equal to 7.5 times 10 to the negative 6. And just to show you that the X is small assumption is valid, the percentage that we wanted to be under 5 in order to make the assumption correct or usable, the percentage is much less than 5%. It is in fact 0.005%. So we are very valid in making the X is small assumption. And so to answer the question, which is what are the concentrations at equilibrium, just take that X value and plug it in to each of those. And what you'll find is if you type into your calculator 0.15 minus 7.5 times 10 to the negative 6, to not write 0.15 as an answer, you would have to have 6 sig figs, because the answer you get is 0.149925. So you would have to have 6 sig figs to not just have 0.15, which is why our X is small assumption was valid. Whew. Okay. We made it. We made it through those. Unfortunately, we are not done with the chapter yet, though. We do have one last topic for the chapter, which is a very important topic. We cannot skip this. This is what we call the Liaise principle, and we will talk about it in the next video.